Recording in progress. Welcome to Lecture 6. This is our first day of materials. Yes, you heard right. Materials are broken up into two sections. Today, materials part 1. We will be dealing with reflectivity, roughness, color. Color is not quite as important as the other two because they are actually what define the type of material that you're dealing with. We don't look at concrete and go, oh, that must be concrete because it's gray, right? Concrete could theoretically be any color because they tint it all the time. Take a look outside in our hallways, concrete floor that's been, coated. But we still look at it and we go, okay, that's concrete. You look at wood and you go, oh, that's wood because it's green or brown or blue. But they can always add dye into the tree as it's growing, or they can add it in after it's done. So reflectivity, roughness, color, what we would call let's see, do I want to bring that up yet? Well, metal materials for today. Metal, and a metal is considered a conductor material. The others are called dielectric. Basically, insulators, to put it very, very simply and bluntly, insulators. On Monday, we'll be dealing with materials part 2. We'll be dealing with transparency, something called transmission, and refraction, also known as glass. And, anything that we can see through. All right, but for today, reflections, something called specularity. Specularity, roughness, like I said, color, and metal materials. Everything else is categorized as a dielectric or an insulator type material. Even glass is considered to be like an insulator. Now, if anybody knows anything about electronics, it's sort of along those lines, where you've got things that conduct, that will allow energy to travel from one place to another on a circuit board, or from a battery to the car, or a battery to power your device. And then we've got things that insulate those wires so that they don't create a short or take the energy away from where it's supposed to go, or the information or data or whatever it happens to be. Little confusing about trying to make an analogy between the two, but it does work. All right, so for today, we've got a Lecture 6 demo files, zip file. After we come back from break, we're going to demo together. I prefer to do it together, but you don't have to. You can always, just watch and then follow along later on and do something. But it's a good chance to practice getting these different kinds of material properties, which is what your main thrust for today is. Also, main thrust for today is finding reference. Finding reference is super important because This is where your creative freedom comes in. You guys lit the interior and you lit the exterior, right? Daytime, nighttime. All of those objects need to have their own material property, or I should say their own AI Arnold standard material assigned to them, and then turned into the type of material that you have reference for. So for example, in the interior, we've got a sofa, we've got a floor, we got chairs, we got an arm lamp, we got walls, we have pillows on the sofa, we have a desk, we have a computer on it, we have lamps. Okay, all of those things need their own material, and there'll be things like brushed metal and fabric and some kind of floor and a wall that's probably painted, or a table that's probably wood, or it could be plastic, or a computer on that table, which happens to be like your MacBook, which is some kind of metal, usually aluminum, because it dissipates heat really well. And it's probably some kind of processed aluminum. It's not highly polished where it's so reflective that it looks like a mirror. That's really distracting and hard on the eyes. So finding reference, super important. We provide you with two pieces of reference. One is the bread for the outside, because this bread shape looks like a potato, was modeled loosely on the reference we give you. And the thermos, which is that thermal container sitting on the desk to the right of the computer in the close-up shot, that needs to be brushed metal, that needs to be some kind of metal thermal container. Basically, it should be stainless steel. All righty. So office hours next week will be Tuesdays and Thursdays. Next week, I will be out of the office on Thursday and Friday, but they will still be in Zoom. And I'll remind everybody on Tuesday again. But you can go to, well, go to Discord like you would normally. Just because I'm not there, we still have 3 other instructors. And Frank will be running the Zoom Open Lab. Frank or Ari will be running the Zoom Open Lab for online and campus students. All right, so just a reminder, project 5 that you did now becomes project 6. Minus the MyComp. That's because having 2 full environments, 2 full different environments, is plenty of work. Please do not underestimate how much work this is. Just because we're giving you 2 lectures and 2 labs to work on this stuff, there is a lot of work to do. Nelson, keep your mask up, please. Thank you. Just make everybody safe. All right, does that make sense? So please don't underestimate. Project 6, when you're done with it, one of the environments in Project 6 will become Project 7. That means we will start texturing. Today, materials, there are no textures. We don't plug anything into the material itself. Nothing, except when we get to glass, because we need to plug in a couple of Maya utilities to get Arnold to give us glass shadows that are proper. But that's it. Everything else, just changing the attributes inside the AI standard material. Today, like I said, your job in lab, find reference, for interior and exterior environments. Okay, start assigning the AI standard surface. I'm just going to call it that. Start assigning a AI standard surface to, well, yeah, I need to refine that, because if I say that, you're liable to think that you can assign one surface to everything and then start changing it. But if you change it on one object and it's assigned to everything else, it changes everything. So start assigning AI standard surface material. Like I said, we will get to glass on Monday, so only worry about the things that are not glass. And we've got all the things specified inside the activity as to what you need to do. There are specific objects that we have that are glass that need to be a certain type of glass. Some are clear, some have color in it. Okay, and we're going to have a couple of pieces of metal, at least. There's the knife in the exterior scene, the one that's sitting in the cheese. And then in the interior, there is that thermal container on the desk. Plus, the computer is also going to be metal. So you're going to get a chance to describe in your materials these different material properties. We're also going to get to anisotropy. Basically, this is brushed metal. And fortunately, Full Sail is filled with brushed metal all over the place. Go into the bathrooms, the towel dispensers, the mirrors, the dividers between the toilets, they're all brushed metal. The kick plates at the bottom of our doors are all brushed metal. Brushed metal behaves very uniquely. In fact, well, that's not really brushed metal. That's more anodized, which is what our computers are. It's intentionally roughed up, but that's okay. We can still deal with it. Yep, that's the same thing. And I forgot to bring my brushed metal, but there's plenty in the room I can steal and show. All right, we're going to get into this thing called BRDF, bidirectional reflectance distribution function. Just call it BRDF. This is how we see reflections, or reflectivity, I should say. Let's do that. From two different directions. All right, so one of those directions is directly looking at it. directly looking at an object. So here's our object. Here's our camera. All right, so when we look at it directly, right here, that is called a 0-degree angle. We're looking at something straight on directly. When we look at our object and look at the peripheral edges of it, and we start to get around to a 90-degree angle, reflectivity looks different. On most common objects that are not mirrors or really super bright chrome, most objects are very reflective at a 90-degree angle, but not as reflective when you look at it directly. This is also called the Fresnel reflection. Okay, it's French, the S is silent, so don't go anywhere and go, hey, I know about the Fresnel. And everybody, when they stop laughing, will show you where the door is. But Fresnel reflection simply means that we see things differently at two distinct viewing angles. Things can also become more transparent when you look at them straight on, directly, and they can become more reflective as you start to look at something transparent at a 90-degree angle. Let's take, for example, I'm assuming everybody's been to a lake or the ocean or a river at some point. You go in, maybe you stick your feet in the water, and you look straight down at your feet. And you can see, usually, if the water's not too murky or too dirty, you can usually see through the water and see your feet. Now, if you're standing there and as you start to look up, if the body of water is big enough, like a big lake or even the ocean, as you start to pick your head up and look toward the horizon, the water becomes less transparent and becomes more reflective. And at some point, it changes over to complete reflectivity. Usually about 30, 45 degrees, it starts to really change because not only does the water get deeper, but you're also getting more reflections from the sky. So by the time you are looking at the horizon, everything is reflective. It looks like a mirror. Does that make sense? So things change in the real world when we look at them at different angles, and that's really what we're getting after. Now, this whole BRDF, Fresnel reflection thing, came into gaming when PBR materials, so gaming has Fresnel reflections. They also have BRDF. Okay, all wrapped up in what are called PBR materials, physically based rendering materials. And that's what gives game engines the ability to really make something look shiny like metal, or now, in addition to PBR materials with NVIDIA's RTX gaming cards, you can now get real-time refraction, reflections, transmission of all kinds of different things. You can get transmission of reflections. You can get stuff just bouncing around in real time. But that's all thanks to these PBR materials. Now, before PBR materials came along, everything was sort of flat, and yeah, you had reflections, but they weren't really genuine reflections. You had shadows. They weren't really, you know, very accurate looking shadows, but it didn't matter. I mean, it was, at the time, it was what we could do in real time, but things have gotten better. All right, so that takes care of the first 3 bullet points there. Just kind of a quick overview. The fourth bullet point is that besides Project 6 and the Project 6 discussion, which is material-based, we have a research discussion that is also due at the same time. So I'm letting you guys know ahead of time so you can start to research what you want to do a discussion on. And it's a research discussion topic. So if you go into 6.3 activity, you'll see that we've got a whole section here about what this discussion involves. So to break it down simply, it's basically a chance for you to research something you are interested in our industry. Gaming, film, simulation, real time, AV, AR, it doesn't really matter. The thing you want to keep in mind is it should be something that interests you, the topic anyway. And there are plenty of databases to research these various topics that you might be interested in. So the ones that Full Sail have readily available are the EBSCO databases, which I understand that you guys have used this before, I think for English or some other composition, some other, maybe it was a psychology even. You've used the Full Sail online databases. Yes? Okay. So personally, out of all the research or out of all the databases, if you go with the complete ones, it's probably going to give you more hits for your topic. Doesn't really matter. You can find any that'll work, but I highly recommend the completes because they are just, they'll go through everything. Now, if you don't find anything in the EBSCO databases, I have 2 approved online journals that you can use. One is called Game Sutra. Anybody here ever hear of it? If you're in game art, you should know about this and you should be there all the time because it is run by industry professionals. And basically what they do is they will do interviews, they will do game release information, they will do what's called postmortems, whereas when a game is released, they will talk about what went right, what went wrong, what basically, what would they do different? Lessons learned, if you will. And it is also, like I said, run by professionals. So it's not just somebody's opinion, it's researched or it's factual because they're actually getting the information from the companies. Now, the other is Game Studies. It's an international journal of computer game research. This is very formal. And this will give you a lot of information, but a lot of it is going to be really kind of theory, scientific based, because this is all about the science of gaming. Not necessarily the art as much, although they do talk about it, but it's more the science. And I basically like to warn everybody now because they utilize a lot of white papers. If anybody's familiar with what a white paper is, it's a researched academic paper that is presented by a person or a group of people that have an idea and they want to talk about their idea and test it and prove it. And they present a paper with all that research that they've done. This is what we wanted to do. This is our method of testing. This is the science behind it. This is the results that we got, 9 times out of 10, 8 times out of 10. It's not necessarily that dry, but I'm just trying to give you an idea. And it always starts in a very particular format. You always start with the authors. They have a little kind of abstract of, hey, this is what we want to prove in our article. This is what we did. Here are the people who helped us. And here are, after this, the results. Now, if you don't find anything in EBSCO, you don't find anything in Game Sutra, you don't find anything in Game Studies, if you find another site, send me the link to it so I can look at it. The whole idea is we don't want a blog, don't want somebody's opinion. You want something that's been researched and it can be backed up with an individual who's had years of experience in the industry doing the job that they're talking about. And it's not just somebody's opinion, or it's so common these days on the web, misinformation. Like people can say whatever they want, and if you want to believe it, you'll believe it. But the idea is for you guys to use critical thinking and comparison and go, okay, that's interesting, but where's the facts or the evidence to back up what you're saying? Does that make sense? Okay, Daniel's saying, I've seen good things on a site called ad.lv as well. All right, send me that in a message if you want to use that, Daniel. And I'll take a look at it, but find me a specific article that you want to use. We'll take a look at it, and if it's good, we can recommend it. All right, now, so this is not a traditional article of you read something and you go, the article I read was all about creating animation for games and blah, 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 blah. What I want is for you to relate yourself to the article that you read. Basically, why did you read it? How did it impact you? Why did you think it was important? Why, if you was it good? Maybe it wasn't good. That's perfectly valid also. Maybe you read it and you thought I was going to get this information, but I didn't. I got this, and I really didn't like the article, but I did learn something. All right, that's perfectly valid. But you need to put yourself in with the information. How does it relate to you? Oh, I've been into animation for games ever since I was a little kid. I started modding. I did this kind of stuff. That's really the information we're looking for. We want to know how you relate to it. You can share that with everybody else, and maybe you'll inspire somebody else to look at an aspect they never considered. The whole idea is to share your information with everybody else. Can we use more than one article? You can, Laura. However, it gets to be a little muddy there. And I don't want it to become overwhelming. So I would just recommend stick with one article, just so it doesn't get to be a really huge project for you. But having said that, if you can do it and you can tie both articles together and do it, in a timely manner and get it short enough where it's not like pages and pages and pages of stuff, that's fine. All right, so we need the article, or we need this research discussion in a very specific format. So the first is going to be the citation. This information is there. Citation needs to be done first, then a link to the article, and then your discussion. Obviously, somewhere in the middle there between link to article and discussion, you want to read it, obviously. Now, link to the article. If you are using the EBSCO databases, you cannot copy the URL above your article. You need to go to the main, like, kind of landing page when you did the article search in EBSCO. When you click on an article, it takes you to kind of the home page. It'll give you a link there. It'll give you a bunch of other buttons. The nice thing about EBSCO is it will create a citation for you automatically. You just tell it the citation format you want to use. And in Full Sail, what do we use? APA, very good, thank you. American Psychological Association. It's kind of a standard format most universities use. It's very specific, but it's, it's fundamental as far as citing something. So APA citation first, link to the article. You use what's called the permalink on that main landing page for EBSCO. If you are using one of the other external links like Game of Sutra or Game Studies, you can copy the URL. URL, you guys understand, that's just the address in your browser. You can copy that safely. The problem with EBSCO is if you copy the URL while you're in EBSCO, that link goes away as soon as you log off or get out of EBSCO. It's only unique to that session. All right, questions so far? Does that make sense? I'm telling you all this so you guys can get a jump on, start researching something that you want to discuss. And it should be something that you get excited about. Why did you come to Full Sail? What gets you up in the morning? Why do you keep doing 3D? Why don't you throw your computer out the window? Because the window's closed. I mean, whatever your valid point is, it doesn't matter. You don't want to break a perfectly good window. All right, so couple of quick screens here. This is kind of what the landing page looks like in EBSCO. They change it occasionally. I took this screenshot a couple of months ago, so I may have to go back and update it. But usually you'll get either a PDF full text or an HTML full text link on the left. On the right, you usually have a citation button somewhere, a permalink button. That permalink will let anybody who has the link look at the article, whether you're logged into Full Sail or logged into EBSCO or not. It doesn't matter. All right, so this is what happens if you don't test your link before you send it to me and you accidentally copied the URL at the top of the page. I get this error. So there will be points deducted if I can't get to the article. Another one is somebody using a white paper that has an abstract at the top, but no link to the full article or the full research document. We need to have that because that is where the actual article information is. And here's one. It's got the citation. It's got the correct link. This one took me to a PDF of, a magazine, and then the discussion. And your topics could be anything. I got lighting down here at the bottom, cinematography, game art, game creation, texturing, rendering. Could be animation, could be rigging, could be visual effects. Doesn't matter, whatever you're interested in. All right, questions? Anybody campus? Anybody in Zoom? Katie's good. Yes. Yeah, go ahead. Well, here's kind of an example. It's going to have the citation, the link, and then the article. That's it. That's the structure. Yeah. Your article could look like this, or it could just be all HTML. Basically a link to another web page. Oh, all right. So you basically want to do this discussion, like I said, using, I like to call it the you component, how you relate it to the article, and weave you into the article as you're describing it. Like, this excited me because, I did this as a kid. I, thought that I was reading about this, but it turned out to be this. And I was disappointed at first, but, I learned this, whatever you relate to it. Just not a recap of the article. I can get that by reading it. I'm interested in how it relates to you. And then you can share that with other people, and they may see this article through your eyes and see it differently than they first thought about it. And that's really the whole idea. Make sense? And if you have any questions, just, shoot me a message or an email and go, hey, this is what I'm doing so far. Am I on the right track? Yep. Good question. So everybody good in Zoom? So Katie, Jerry, Joshua, anybody else? Take a screenshot in case I missed anybody. All right, I see Nate, you came in, so I'll have to get you later on because we already did attendance. All right, so let's go on and start to talk about material properties. So we went over this type of material in lecture 2 when we started talking about lighting, because in order to have lighting work, you need 2 other components. You need what? You need an object, camera. So we need object, camera, light. What's that? Yes. So you can just say light because we know that it's going to be a light source. But to make something visible in the real world or in CG, those are the 3 components. Like we can have light, but not necessarily know where it's coming from. Granted, most of the time we know, hey, it's the sun, I'm inside, it's an artificial light, it's something else, I'm bouncing something, I'm bouncing sunlight off of something to another object. But what we're interested in for this part is this type of material that our light is hitting. What kind of reflection is this? Well, it is, well, not necessarily true. That could be direct light on there. Remember, don't think about the light itself. We're thinking about the light is hitting this surface. That surface is displaying diffuse. Yeah, that's it. Good. It is a diffuse material or surface. Now we get this reflection. Remember, if light were being absorbed by the material, it would look like a black hole. If it were reflecting it really strongly, it would look like a mirror, or it would look like, a shiny object like chrome or highly polished metal or really shiny plastic. But this object has microscopic irregularities, basically really, really fine roughness that may not be distinguishable to the eye, but if you put it under a microscope or even a magnifying glass, you could probably see the little pitted areas in there. And when light rays come in and hit it, they hit those little pockets, little bumps, and they start bouncing around in all directions. They diffuse or scatter. And that's what causes this type of reflection. Now, when we have a surface that is smoother, we start to have organized light rays coming in and organized light rays reflecting off of the surface. So here, for example, we've got a mirrored surface. Wouldn't say perfectly smooth, but really, really smooth because we see reflections of environment and we even see reflections of light sources. Now, this has to do with a couple of things in CG. One is the angle of incidence. Where is that light coming in? Light ray always hits a surface at some angle. how do we measure how the light hits, say, for example, a poly face? We have a sphere. It's made up of a whole bunch of tiny little polys, or maybe not so tiny, depending on how many subdivisions you have. But it hits a surface. How do we determine what the angle that the light hit it, or another object collided with it, or a particle hit it, or basically anything? How do we measure stuff? Yeah. That was the question. Okay. So the question is, how do we measure anything in CG when one object affects another object? Object in this case could be light. In gaming, it's collisions. How do we decide where one object intersects another object? How do we decide where a particle hits a surface and bounces off of it? Because in CG, we have to calculate everything. We have light coming into our surface. It hits the surface, it bounces, but how do we know where to send it when it bounces? How do we know the angle that it came in at? How do we calculate global illumination? It's not like some magical thing, higher math that's beyond everybody. It starts off fundamentally at the poly surface. All right, so everybody thinks this is a lot more complicated and I'm being verbose about everything. But let me open up Maya and show you guys something that you are all familiar with. I could say one other thing, but if I do, I think that's like giving it away. So let's try this approach. Come on, Arnold. Good. Okay. So let's create a simple poly surface. Okay, polysphere. Let's zoom in on it. And let's see. Let's look at it from, we'll say, the front. So I want to look at it from the front. So go to orthographic front. There we go. So let me zoom in here. And let me go back to perspective, and I want to show my front camera. So I'm going to unhide it. And hopefully I can see this. Where is it? Oh, that's right. Maya makes all these weird things. Never mind. Let me just make another camera. It's a whole lot easier. Create a new camera. There we go. So there's my new camera. Let's use that. Let's look through it. Let's zoom out. We'll look at it directly right about there. So in perspective, there's my camera, there's my object. Right, so let's create a light source. And it doesn't really matter. Let's just pull this over here. And let's put our light source here. Let's put it here, just for fun. Okay, really where it's at doesn't matter. But, so how do we calculate where the light source is and where the camera is? Let's look through the camera. So we look through the camera, I can't really see my light source. But if I render it out, in theory, I should be able to see it. There it is. It's off to the side. Now, How do we figure out where everything is in 3D space? All right, so we have our polys on our surface, on our sphere. You guys familiar with this? What are they? What's that? Yep, they are face normals. Every polygon has a normal. The normal is always perpendicular to the polygon surface. Remember, polys are flat. If you want to make something round, you need a whole boatload of little polys to make something appear round. But every single poly has its own normal, its own face normal. That tells the camera, that tells the light, that tells anything where it is in 3D space, where it's pointed for one thing, which makes a huge difference for texturing. You guys have all laid out UVs, right? If your normals are flipped, what do you get? What's that? A reverse texture, or it turns up black. It doesn't show at all. So the normals need to face outward so that light can come in, it can hit it, it can be calculated, so that when we're looking at a texture, we know where it exists on that whole surface. Remember, every normal is associated with a poly, and every poly's got a little UV patch that goes with it. So it can be described with texture at some point. Right, does that make sense? So we can tell where this light is based off of its relationship to the camera and the surface normal that it hits. So we get a light ray coming in here, hits, and then at some point, this is going to bounce back into the camera. And when we render, this is what we get. Now, obviously, if I want to make it brighter, so all those normals are telling the camera, they're telling the renderer, they're telling the light where it exists in 3D space. All of that information is really important when we start calculating reflectivity. So we have a light ray coming in, it hits the surface. It bounces back at the opposite angle. But like I said, it's all about that relationship between the surface and the normal. So if a surface is really smooth, if we're telling that surface in CG to be really smooth, like glass or a mirror or highly polished metal like chrome, right? The angle of reflection is going to more or less mirror the angle of incidence, that incoming light ray. So if this light ray comes in at, say, 45 degrees, we'll say it's positive because it's probably above the axis there. And it might come in at like negative 45 degrees, or it might go out at negative 45 degrees. Does that make sense? So remember, everything's got a surface normal. Whether you choose to display it or not is another thing. But this is what goes on behind the scenes on our objects all the time. And that's why if you've got an object that's not displaying properly, it's always a good idea to check the surface normals. See what they look like. So if I come back here, let me turn off face normals. So if I come in here and I reverse these normals, let's go, oh, mesh, no, display, there we go. Let's reverse it. So now all the normals are facing inward. So if I turn face normals on this, you can't see anything. And this is just using the viewport. Remember, the viewport's got a camera. The viewport's got a light in it. That light lets us see what's going on in the viewport. Without that light, you wouldn't be able to see anything in the viewport. It would be totally black. Now, where are the normals? Well, the normals are inside the surface here. They're facing the wrong direction. So when the camera's inside, guess what? They display properly. They're reflecting light. But outside, they are not reflecting light. So once I reverse them back again, now it's totally good. I go inside, totally black, because the normals are out. So those surface normals help us to be able to calculate where light is coming from in relationship to the object and the camera. So smooth object will display organized light rays bouncing off of it, meaning they don't get all diffused because the surface is not rough like it is on a diffuse surface. It is a lot smoother. Now, in addition to getting images of the surroundings, environment reflections, we also get direct light sources. So for example, here, our highly prized poly surface. Let me assign a AI standard material to it. All right, so AI standard material has specular turned on. We had you guys turn it off for the first 5 exercises because we just want flat gray. We basically want matte, we want a diffuse surface, so we're not distracted by shiny or color or visual pattern on it. So if I render this out again, let me hang on to that, hit the render button. This little highlight here is a result of that spotlight hitting the surface and then finding its way, the light found its way into the camera. So for example, let me go stepping away from Zoom for the moment. Everybody in Zoom, be right back. Is very reflective and smooth, the glass portion. So if I move this around, at some point you should be able to see the light from the projector hit it, and you should be able to see it directly. Right? You guys can see that little round dot, that's the light, correct? Okay. So that means the light from that projector hit the screen, and at some point, all the bounces that are coming off of here, some went directly into your eye. And that's why you see direct light highlights like this. Or sometimes called specular highlights. Right, so everybody in Zoom, real quick, all I did was show the reflectivity of my phone. And at some point, when you have a direct light hitting a shiny, smooth surface, it bounces off and goes directly into your eye or the camera. That's what this specular highlight is, direct light. all made possible because the surface is smooth. Now, an average ordinary reflective surface is called an isotropic reflection. And it's based on three main components. One is the base, that is the color of the object. Most of the time for us, it's been gray so far, but it could be any color. So base, or a diffuse reflection. You add on actual reflections, environment reflections. You add in specular highlights, those direct light highlights. And the final result of that surface is an isotropic reflection or standard issue. You can see some environment, you can see light in it. That's an ordinary average reflection. So we have isotropic. Come on, there we go. And then we have something called anisotropic. People really get confused when you add the an in front of it. If you can say isotropic, you just put an in front of it, anisotropic. Anisotropic simply means that there is intentional roughness in the surface and that the reflection, the angle of reflectivity changes based on how the surface is aimed at the camera or rotated. Let me see if I can find. Well, be right back again. I don't know if I can. Let's see. Can I do this all the way over here? So let me see. Let me stop sharing. And let's go here. And spotlight this. Oh, of course, can't see it because there's a podium in the way. Nice. Thanks, Full Sail. Wonder how long I can pull this off before it falls off of the table. All right. So what I'm going to be doing for anybody here is walking over to the door with my phone and showing what an isotropic reflection is. First, I'm going to do it on the board, and then I will do it over by the door near the kick plate. Okay. So we already established that you guys can see a reflection from the projector and my phone, right? I turn my phone. Does the reflection or that highlight, that round highlight from the projector change? No, it stays round, right? Pretty much. However, if I go over to the door here, and the kick plate on the door has intentional roughness, do you see that long streak of light down there? It's a vertical streak of light, right? Now, if I turn my phone, that streak doesn't change, but the reason that it's not round like it is, here on my phone, the reason it's not round is because there is intentional roughness on that kick plate. That roughness is horizontal. They crush the metal, the stainless steel, when it comes off the line. The reason they do that is it tends to show less fingerprints, less dirt, less all kinds of stuff. So that intentional roughness translates to a vertical highlight. An anisotropic surface always has a stretched direct light highlight perpendicular to the roughness. So any kind of brushed metal surface like that you can actually see the lines in it, any kind of brushed metal surface like that, if they're horizontal, you'll get a vertical line of light. If it's a vertical roughness, you'll get a horizontal line of light. It's always going to be 90 degrees from the roughness. Does that make sense? And if you turn that object anyway, it will change because the roughness angle is changing. If I were to pick up the door and turn it 90 degrees, my highlight would shift with it. All right, let's see if I can put this back without completely killing everything. Ooh, that's a scary person there. All right, let's unhighlight this. Yeah, let's remove that spotlight real good. And let's go back to gallery. Oh, and while I'm at it, let's share the screen again. All right, so let me ask you a question. Since that was a grand experiment, could you guys in Zoom see that at all? All right, you could see it. Good. Okay, I'm hoping it recorded. Just really hard to hear, yeah, because I had to leave my headset at the desk, considering it's like 2 feet long and that door is about 20 feet away. All right, so that worked, sort of. All right, so that's really just trying to give you guys the idea of the difference between isotropic and anisotropic reflection. Now, last year, we were doing some Unreal training, and we went to, it was called Unreal Fest. They had it this year also. Basically, once a year, they put together all these virtual seminars that you can go to for free. And we went to one of them on materials. And when they were talking, they basically brought up everything that we find every day in our students' work. And they were complaining that a lot of times they will get artists that come to them, they see something white, they immediately make it pure white, or they see something black and they immediately make it pure black. When in reality, there is no pure white and there is no pure black. So what they did was they took some pictures they took a piece of charcoal, something really dark, took a picture of it. They took a picture from somebody who went out on vacation, snowboarding in Colorado, took a picture of the snow. They took them into Photoshop and they measured the brightness of those surfaces in Photoshop. And they found, for example, that charcoal wasn't really pure black, which would be 0.00. They found that charcoal was 0.02, which makes it really dark gray. Where they found the white of the snow wasn't really 1, which 1 is considered pure white. They found it to be, they said, between 0.8 and 0.9, somewhere around there. So one of the first things that you can do as an artist when you go to add color or even adjust the value in your color is realize that nothing is ever pure white or pure black. It's always going to be really light gray or really dark gray. And that tends to make things look more realistic. Does that make sense? All right, so this is a really good thing to have as reference for you guys. So when you're looking at your reference images and you see something, oh yeah, that's a white sofa. It's not really a white sofa. It's probably going to be really light gray. Or, oh, that's black leather. It's not going to be really black leather. It's going to be really dark gray. All right, so with that in mind, let's take a look at for example, my mouse. Generally, I use a tablet and a pen, but I also carry a mouse as a backup. Why? Because stuff breaks all the time. All right, so here is the mouse that I use to take these pictures. This was at my desk in my office, and I have above my desk, I have a big rectangular fluorescent light, which happens to look exactly like this. The reflection on the edge of my mouse, right here. And you can see this area right here is super smooth. Look at the detail in the reflections that you can see. You probably can't see a whole lot from back here, but I'll walk over to the projector in a minute. But the whole idea is this surface right here, this mouse is actually made up of several different kinds of surfaces, several different kinds of material properties. As a modeler, you would model this like it existed in the real world, right? You'd have buttons, you'd have a wheel, you'd have an area at the bottom if you were modeling this that had a little cover for the battery that you could remove, or at least you would put the detail in there for it. Whether it actually opened up or not is another thing, right? And also on the sides of most, consumer grade mice, you will see kind of a rubberized grip on the side. It's kind of like the same thing I have on my tablet pen here, right? Just non-slip, meant to keep it from, slipping out of your hands if you get a little sweaty. Now, they all exhibit, the reason I like this mouse is it exhibits 3 different kinds of material properties. One is super smooth plastic. This would be considered to be a low roughness surface. Why? Because we can see detailed reflections that are not all that blurry or cloudy, misty, whatever kind of verbiage you want to use to describe it. Hard, smooth, sometimes called a high glossy surface. Sometimes people will use glossiness, sometimes they will use roughness. Depending on the software package you use, it could be either. Most of the time, roughness is what you'll find. But if you're working in some kind of weird package for somebody and there is no roughness, but there is glossiness, that's your roughness. Now, it's really weird because Arnold uses roughness, RenderMan used roughness, but we had V-Ray for a while, and V-Ray would have roughness and then you could turn a switch and it would change it to glossiness, which was really weird. Why you would put both in, I have no idea. But I guess they got so much complaints from people that, hey, I'm used to glossiness, I want glossiness, but I want roughness. So they gave you a switch. But the problem was, when you switch from roughness to glossiness, it was the opposite of what you wanted. So just be aware, software packages are always going to be a lot of fun, depending on what you're doing. So low roughness, sharp, detailed reflections. Take a look at the next screen here. This is the button area of my mouse. So now, same light, same environment. The only difference is the surface itself that's reflecting. So notice that my light is no longer sharp and detailed. I can't really see much in the environment. I can see vague shapes. This would be considered to be a medium to high roughness surface. blurry reflections, low surface glossiness, soft highlights. They could all be used to describe that. And then on the sides, this would be considered to be very high roughness because that same light now is so spread out, it's not quite to the point of being a diffuse surface. All right, so a diffuse surface, which I actually have here above it, this is basically my cloth hat. So you can see that it's diffuse no matter what I do to it. It's kind of like carpet or fabric, like my hoodie, t-shirt material. They all really are diffuse surfaces because they have the little fibers that kind of bounce light all over. So cloth, this is totally diffuse. Total diffuse. But down here, this is the rubber grip. Not to the point of being diffuse because I can see some of the light. Even though it's really blurry, I can still see some of that light. Can't really see much else in the environment, but that light is still there. So very soft highlights, very low amount of surface glossiness, high roughness. All right, so in the real world, I'm going to switch back over to the board again. So in the real world, I don't need my map. My phone, need my map. So here, there's my nice little shiny light from the projector. Really nice detail. You can see it's sharp, it's bright. As soon as I move my mouse down, you can see that the rougher surface spreads that highlight out. I can't really see much of the environment anymore. Then when I shift it to the side, it spreads out even more because this is rougher still, this rubbery side to it. Does that make sense? So 3 different types of material properties, 3 different kinds of reflectivity, same light source, when it hits a different material. If you can understand these 3 things, that's the basis to pretty much describing any other material other than metal or glass. Well, glass even, because glass has roughness on it too, but we'll get to that on Monday. But the idea with this is any surface you look at. So for example, all the desks you're now using for your computer. If you stand up and look down on them, they don't look that reflective. But if you sit down and look to the side or put your face close to it, take a look at it, you can start to see some reflectivity. So that will tell you, looking at a surface from different angles, that'll tell you whether it's truly diffuse or it's got reflectivity in it. Now, true diffuse surface like carpet, I don't recommend you putting your face near our carpet. But you get the idea. I look at it from many different angles. I really can't see any kind of sheen or any kind of light bouncing off of it. Spread out, it's diffuse. All right, so we were just looking at my mouse a little bit closer with the projector highlight, and also talking about the desks that we have here at Full Sail. All right, so basically, if you can understand these 3 different kinds of property, you can describe a lot of different materials in our everyday world. Something that's very smooth, something that's not as smooth, but not super, super rough. So it's a diffuse material like a hat. Rubberized surface, which is rougher still, but still not to the point of being diffuse like the hat. right? Those levels of roughness really define the kinds of materials we see every day in the real world. And in your reference, you may have something that doesn't look very reflective, but I highly encourage you to get additional reference of that object from different angles if possible, because it may not look very reflective when you look at it straight on, but it may be pretty reflective off to the side. Now, when we're dealing with the AI standard surface, we've got the base section, we've got specular, and we've got transmission. So the base section, this is our diffuse. The specular section, this is our reflectivity. That's reflectivity. And down here, transmission. This is basically our refraction section. So all three of those together can have 100% of the energy in your scene. For projects, basically for most of projects 1 through 5, all of the energy's been in the diffuse part of the material. We haven't had anything reflective on except for the skin texture on the portrait. When we start to add in reflectivity, we are stealing energy from the diffuse. Remember, to make something physically accurate, you can only have 100% of the energy in any one place at any one time. So if something's not 100% diffuse, it's got reflectivity, it's no longer 100% diffuse, it's less, and that other portion is offset in some other channel in the material, like reflectivity. Now, the thing about Arnold is, when you create that AI standard surface, you don't automatically get 100% reflectivity, even though it may say specular weights all the way up, the color is white, all the things point to the fact that it should be like a mirror, but it's not. It's limited to a certain point to be reflective. There are other controls to make it look more like a mirror, which we'll talk about. Now, we've got basically artistic mode versus physical mode in our AI standard material. They're not directly called that. We call things artistic mode because we as artists will say it's that amount of reflectivity, it's that color, rather than just using physical numbers that have been measured in a laboratory. Now, let's define, we talked a little bit about conductor materials and dielectric materials. So let's kind of recap this one more time. So dielectric materials are things like paper, porcelain, glass, plastic, air, rubber, wood, concrete. It's pretty much a dielectric material. Anything but metal. Metal are the conductor materials: steel, copper, aluminum, iron, gold, silver, brass, bronze, zinc, stainless steel, titanium, you name the metal, it falls under this category. Now, there's two different ways to tweak the controls based on whether they're dielectric, which is everything but metal, and then they're metal. Fortunately, in Arnold, it's not really that big a deal because Arnold's actually got a slider called metalness. Convenient enough. So Dielectric materials, those are everything but metal. We adjust the base color, the specular weight, and the specular color. Now, having said that, it's kind of misleading because we never adjust the specular color unless it's metal. We'll get into that in a second. Conductor metal materials, well, first thing we adjust is metalness. Turning metalness all the way up makes the material behave like a metal surface. Metal materials are inherently less reflective on the edges and more reflective in the center, whereas the opposite is dielectric. Dielectrics are much more reflective on the edges and less reflective in the center. So we adjust the metalness, the base color, the specular color, all contribute to the type of metal. And then, of course, there's specular weight. So a lot of overlap in these controls, but it actually makes sense when you start to do it. Now, in the world of metal materials, there are two kinds of colors in metal. There's what we call white metal and red metals. So how do you know if something's white? How do you know if something's red? It's actually not that hard. Anything like copper or brass or bronze or gold, those are considered red metals because red is the primary color that's being reflected back when you look at those metals. Now, most of the time in our lights, we deal with white lights, right? Kind of neutral lights. When you shine a neutral light on a red metal, you get more of the orange and yellow and red reflected back at you, and the other colors are absorbed a lot more. Whereas with a white metal, like steel, aluminum, silver, titanium, stainless steel, you get more of the RGB rays coming back equally to you. Now, they may look kind of gray. Some people say it's gray, it's silver. All right, those are all characteristics of a white metal. Does that make sense? Now, if anybody's interested, I've actually got a link to a document inside lesson 6, which is right here. Why is copper reddish in color? So this is a company that manufactures metals, and they also have a lab to test the purity of the metal, which they do in a lab with a different materials. They measure refractions and they measure color. And basically, the first page is really simple. The first page just basically says what I said right here. You can take a look at it. If you're interested in the math, they get more into the math back here, and you can see. But the bottom line is we see orange, we see gold, we see yellow, we see red, because those are the colors that are mostly reflected back. That's why we see red in a sphere. When I had that red sphere up there, right? Those are the colors that are primarily being reflected back. So all of that means that in order to make a red metal, we need to add a little bit of color in the base color and also in the specular, because gold, brass, copper, bronze reflect back that color, whereas the other metals reflect back all the bandwidths. So things look more orange, look more gold, look more yellowy, look more bronze, brass, whatever you want to call it. All right, so dielectrics, base color. This is the object color at the 0-degree incidence, facing the camera. So remember, we've got 0 degree, which is us looking directly at an object, and we've got 90 degrees off to the sides. So when we look at something directly, that's our base color. Specular weight, this is the brightness of the specular highlight. How reflective is it? How reflective? Specular color, this should be white for all materials except red metal. Emblazon that in your eyelids when you close your eyes at night. Because one of the things you can do to really make something look artificial and not look realistic is to put color inside the reflected color back to the camera. That just breaks the physical accuracy of the material. So remember, dielectric materials, this is everything but metal. Everything but metal. Now, we get into making metal. So we got an extra control in there. That's the metalness control. So you turn, if you're making metal, you generally turn this all the way up. All the other properties in metal are going to be controlled by the base color and the specular color. Now, base color, this is what does the metal look like facing the camera. Should be gray or white for all metals except red. Specular weight, that controls the edge reflectivity only. When you turn up metalness, 0 degree is handled by the base color. And that amount of reflectivity is handled by metalness. But the specular portion of a metal object controls the sides. So specular weight controls the edge reflectivity. Specular color controls the color of the edge. It should be white for everything but red metals. So when we make gold, when we make copper, when we make brass, when we make bronze, we put a little bit of color in the face and the edge together. That way, that's how we get the color in metal. It's the reflected color back to the camera. It'll make a lot more sense when we actually demo it because you'll be able to see it in action. Right now, this is all just trying to give you a brief overview so you can kind of get a handle on why this stuff is so important. And one of the other biggest things is we do not use pre-done materials. So no material presets. We make all materials from scratch. Why? Because if you go somewhere to work, they're going to say to you, okay, you can say, oh, we want gold. So you go, you find a pre-done gold material. Maybe you use Substance Painter and use one of the Substance Materials or Substance Designer. You bring it in and they go, yeah, but that's not the color of gold we want. It's got too much reflectivity. They're going to want you to change it. So you better know how the material works so you can actually change it. Presets are good if you're doing something quick for proof of concept. But when you get down to the nitty-gritty and actually have to make it for either a game or in film or TV or some other medium, you better know how to fix it and how to make it look good. Because when you throw it into an environment with light and camera and all the other things going on in the scene, it can either look really good or really bad if it's not done right. So make your own materials from scratch. This goes for anybody online watching this also. No material presets. There's tons of libraries out there, which are all great. But if you don't know how to make a material from scratch and alter stuff, you will be at a total loss when it comes time to do something on your own. You'll probably burn up more time trying to find a material to replace the one that you thought was really good, rather than just going, oh yeah, let me just adjust this. All right, so roughness, whether you're doing metal or plastic, is still the same control. It's under specular. There is roughness under the base called diffuse roughness. I'll show you what that looks like. That's mostly for things like suede or felt or maybe even velvet. It kind of gives you almost like a powder coated look. If anybody's ever seen powder coated metal, that's kind of what it reminds you of. You can definitely tell it looks a little on the fuzzy side. Not quite completely, but that's kind of the general impression. So the default in Arnold for the roughness that you get is 0.2. That's actually quite rough. So just be aware that you're probably going to want to go, if something is pretty clear, it's definitely going to be under 0.2, might even be under 0.1. But nothing is perfectly clear. There should be no zero roughness, like maybe 0.01 will add just a little bit of realism into any object. You start getting into things like brushed metal, frosted glass, then we're going to crank our roughness up beyond 0.2 because it needs to be a lot rougher. So we talked a little bit about anisotropic materials. So to make an anisotropic material in Arnold, once you make it metal, it's really easy to make it anisotropic. So for example, the brushed metal I got here, you can see my color for the base is a little bit on the gray side because that's stainless steel. I got that, I got all these measurements and stuff from the internet, and I'll show you where it's a good place to get them. You'll notice the weights, at 1, the color is white because they're stainless steel. It's going to be white metal. And in order to make it anisotropic, down underneath, under roughness, under this thing called IOR, which is grayed out here, you'll see anisotropy and rotation for the anisotropy. So I have 3 renders here. This one in the middle is just the base roughness here and the base metal. 0 degree or 0 amount of anisotropy and 0 rotation. On the right, I've turned up anisotropy, but I left the rotation at 0. So the highlights and the reflections almost look like they come a little more into focus. They're not quite scattered all over the place. But in order to make something brushed metal, most objects like this have a horizontal brushstroke on them, which means you want the highlights to stretch vertically, which means you want the rotation to be at 0.25. Here's the downside of Arnold. Arnold rotation is usually in degrees. We think of that all the time. But in Arnold, rotation goes 0 to 1. So 0, 90 degrees would be 0.25. 180 degrees would be 0.5. 270 degrees, which I'm running out of room here. Come on, get out of the way. 270 degrees would be 0.75. And if you go 360 degrees, you're back to 1. So most of the time, you want your anisotropic rotation to be 90 degrees from 0, which is 0.25. So anisotropy at 0.95, I don't quite have it turned all the way up. It always tends to look a little better if you don't go all the way to the max. But again, that's your call. And rotation at 0.25. So that gets you the stretched highlight that you would expect from an anisotropic material. And like I said, this is all under specular right here. All right, so we have a couple of resources for you guys. We've got some reading, we've got ray tracing, I've got the standard surface Arnold Maya user's guide. That'll tell you pretty much every little attribute inside the Arnold material, what it does, what it looks like. Let me show you. So we go here. You come down under here, standard surface. You'll notice that here, if you want to look at just what the specular looks like, or sorry, the base, this will tell you what it looks like. Metalness, roughness, color, which is pretty simple to get a hold of. And then down here under metalness, they show you what, aluminum, copper, gold, and they've actually gone and they've sampled colors. But I'm going to show you how to sample colors from your reference images. Because these are fine, but you're always shooting for a photo of something that either the client gave you or your boss gave you. And it's good to have this kind of stuff, but honestly, we don't use RGB colors. We use HSV, which is hue, saturation, and value in Maya. As an artist, it's a lot easier to think of color. How dominant is the color, and is there light and dark in the color? Rather than what's the level of green, red, and blue for that particular shade? That gets to be a little crazy. Question? Oh, okay. All right. A whole bunch of other stuff too. I mean, if you want to find out what each section does, I highly recommend. This is a good reference link. I use this all the time if I can't remember what something does or how I want to do something. Especially if I go into a section that I don't use all the time, like subsurface scattering or one of the other sections. So it's really good. Now, refractive index database. This is actually the greatest thing ever. This will give us the equivalent of what we need to make accurate metals. So we've got base color, which is our 0 degree visibility. And we've got our spec color, which is, or our specular in general. Specular color, yeah, specular color. This is basically how reflective and what color is that reflection at 90 degrees. So if you understand that, getting the information off here is a lot easier. And I'll show you how. So here, by default, in this refractive index database, This is set up sort of like a library. A mythical building where you go and there used to be books, and you go to a shelf and you go to a category and you pull the book off the shelf. Unfortunately, most people don't use libraries anymore. So it's really hard to make an analogy if you've never been in it, but you can see that we're doing simple inorganic materials. The book is silver. We're learning how to make silver. And basically, this is the recipe for silver. This was silver as it was measured in a laboratory in 1972. You don't like that? Well, you can go find another one down here, like one of these later. Now you can see that it changes these numbers down here, refractive index, extinction coefficient, when I change the recipe for the metal. Now, these numbers don't mean anything to us in Arnold, but down here underneath, there's an area called reflectance calculator. This means a lot to us. So remember how I said when we're doing metal, if you're doing white metal and even red metal, you're going to figure out what is my color at a 0-degree angle. Well, you'll notice down here under reflectance at 0 degree, it is 0.991. It's not 100% white. It's very bright, light gray. So for example, for silver, so our base color here would be 0.991. And that would be the value. The color is still going to be white. Saturation is still going to be 100%. So in our hue, saturation, and value, the color is going to be white. Saturation is going to be, well, you can turn saturation all the way down, which for the most part it usually is. And then this will be your value control. Now, at a 90-degree angle, if I hit enter, notice that at 90 degrees, it is pretty much pure white. It's really reflective. Now, if I go up and change this to another metal, let's go to aluminum. Notice that my recipe down here changed. So at 0 degree, it's now 0.965. Remember, silver was 0.991. This one is a little darker, 0.965. This goes into the value of your base color. And then at 90 degrees, it's at 1. Honestly, most white metals are 1 at 90-degree angle. But you may as well figure it out while you're here. Now, if you want to go something that's a little more, well, let's go chromium. Chromium. So down here for chromium, let's go 0 degree. Notice for chromium, chromium's pretty dark. Chrome is 0.579. That's a lot darker. That's almost 50% gray in the base. But the 90 degree, that's the specular color, is still going to be 1. It's going to be bright. Go down here for something like, let's go titanium. Do we have that here? Yeah, titanium. There we go. So titanium. Go down here for 0 degree. That's looking directly at it. It's 0.625. At 90 degree, it's going to be 1. And this is basically how we can pull the numbers to get the proper kind of metal, to get the proper amount of reflectivity in the metal. Now for gold, let's go back up to the top here. So for example, if we want to do gold, gold is going to be 0.979 for 0 degree and 1 for specular color or 90 degrees. For this, you would have to sample the color for gold off your reference. And the color for one gets plugged into base, and then the edge color you plug into the specular color. Like I said, this will make sense when we actually go and make metal. It's really not as hard as it sounds. But this is a really good index to have for making different materials. All right, let's see. So we talked a little bit about BRDF. So in today's rendering, if you guys are going to start rendering, we're going to be starting to crank up the specular samples in your render settings. Because now, once we introduce reflectivity, Arnold is going to start showing noise in reflective surfaces. Now, you're still going to have your camera AA. That's still going to be what you did normally for a render. Put it at 4 or 6, right? Diffuse is still indirect light. That's still going to be bounce light. That's still going to be 6 or 8, somewhere around there, especially for these big scenes. Now, you may have them look perfect, and it looks really good when you did your lighting. But as soon as you start to add reflective materials, you may notice noise in the reflected areas. That's where you start to increase your specular here. So just like all the other settings, medium quality is 4, kind of medium high quality is 6, and high quality is 8. Just be aware, if you crank everything up to 8, you will be here for a long time rendering. Because when we start to add in more components to the material, it's going to take that much longer to render. So be careful with the diffuse, the diffuse is always going to be high, but be careful with the specular. When we get into glass, you're going to be worrying about the transmission also. So metal, glass, shiny objects, lots of color, that's all going to start to grind your render times. Or I should say, make your renderer grind slower and increase your render times. So if you have a little bit of noise, try spec at 4. That usually works pretty good. You might need to go 5, maybe 6. But just remember, every time you increase it, you're adding a lot more samples. All right. Good time to take a short break. That'll give me a chance to render out the first part of the lecture. We come back, we'll demo. You guys can follow along if you download that Demo6 project folder that I have uploaded inside the activity. So download this one for sure. I'll go over this other stuff and show you what that is. Let's see, come back at 3:15. Anybody have any questions before we go on break? How about out there in the Zoomosphere? Questions? All good? All right. So I will see you guys at 3:15.